Today I'm be talking about chassis stiffness and the effect it has on vehicle handling. You may see advertisements for trucks where they talk about how the front and rear or the front cab and the bed have different angles, so the chassis flex. Or you may read about race cars and how they need a stiff chassis. Well, I thought, how stiff does a chassis need to be? So I started doing some research. Started off with an Excel spreadsheet. We have chassis stiffness, front and rear roll stiffness, and then the CG height, track, weight of the car, and a lateral G to calculate weight transfer. So using those, I got weight transfer of the front and weight transfer of the rear. And if you do a percentage of how much it is front, you get a lateral load transfer distribution. In this case, 50%. If you increase the rear, then you get a less front lateral load transfer distribution. The roll resistance is more on the rear. And this number is not taking into account the chassis stiffness. So that's just as if the chassis was infinitely stiff. So I created this chart, which takes front and rear roll stiffness for different roll stiffness distributions, and they all equal the same roll stiffness overall. But I added the chassis in series to the front suspension. So to get a springs in series is one, the reciprocal of the reciprocals of them headed. So here the chassis stiffness and here the front suspension stiffness. So that's the number here. So if you increase chassis stiffness, that number will become closer to what the roll stiffness is. So a very stiff chassis, it's you're getting closer to your theoretical number of the chassis being infinitely stiff. But we all know that's not the case. There are no chassis that are infinitely stiff. But I got the with the different chassis stiffnesses, I got the different lateral load transfer distributions for each roll stiffness distribution. If we take that table and create a chart, this is what we get. So we have roll stiffness distribution and then the actual lateral load transfer distribution for different chassis. If we look at the very stiff chassis, so not infinitely stiff, but very stiff. For the roll stiffness distribution, we get 40% lateral load distribution for 40% roll stiffness. 50% roll stiffness distribution, we get 50% lateral load transfer distribution. So that's what we'd expect from our theoretical numbers, where we just look at suspension and we don't take chassis into account. So let's say you want your lateral load transfer distribution to be between 45 and 50% front, using your springs and anti-roll bars to achieve that. So you would need between 45 and 50% roll stiffness distribution to be able to tune to that range. Looking at a less stiff chassis, we'll say the one that's 1,500 foot-pounds per degree, to get between the 45 and 50% lateral load transfer distribution, we need right around 49 to almost 55% front roll stiffness distribution. So for the same lateral load transfer distribution, we need a larger range of roll stiffness distribution. So I went to my chart and I made what we'll call a chassis stiffness factor. So it's the stiffness of the chassis divided by the stiffness of the suspension. So it's how many times stiffer is the chassis than the suspension. So we can make the same chart just using this chassis stiffness factor instead of the foot-pounds per degree number, which this can relate more to other cars, not just this single one where we're looking at specific roll stiffness and chassis stiffness. So I made another chart that's using different roll stiffness. So the overall roll stiffness is lower. Same roll stiffness distribution as the other chart, and then the chassis stiffness factors the same as the other chart, which you see is lower chassis stiffness numbers. So if we plot those two tables, we get each one has the same chassis stiffness factor, and we can see they overlay each other. So looking at this method, it's showing that for the different lateral load transfer distributions and the range of roll stiffness distribution, the relation of chassis stiffness and roll stiffness are the same. So a lower chassis stiffness factor is going to need the larger range of roll stiffness distribution to get whatever your desired lateral load transfer is. So this shows as you increase your suspension stiffness, you're going to want to increase your chassis stiffness to be able to get to your theoretical values of the calculations that don't incorporate chassis stiffness. But what these don't show is vehicle weight. How does that play into all this? And how does this is all steady state? How does all this apply into transients, like your turn in on a corner? So I got out of Excel and then I looked at a transient dynamic model, which incorporated weight damping and the chassis stiffness and suspension stiffness. So we'll look at that next. So for this transient model, I split the chassis into 3 sections. Each section has its own rotational inertia and torsional stiffness. And these are once again in line in series with the suspension. Since there's 3 different sections, I have 3 accelerations for the front, middle, and rear. And these are taken from a different transient model, which showed that since the lateral force starts with the front tires turning, the front sees acceleration before the rear. And I fit a polynomial to that raw data to be able to use in this simulation. So like in the Excel model where I did a chassis stiffness factor, which it just normalizes the chassis stiffness to suspension stiffness, I did the same in this except with frequencies. So taking the natural frequency of the suspension and the natural frequency of the chassis. So you divide the chassis frequency by the suspension frequency, and then we get a frequency factor. So unlike the static model I used in Excel, which just took stiffness into account, the frequencies take stiffness and mass into account. So this first chart is just different inertias with a chassis frequency factor of 2. So the natural frequency of the chassis is 2 times that of the suspension. And for different inertias, we can see the lateral load transfer distribution over time, they all match. They all follow each other. So what this tells me is you need to look at inertia and stiffness. And just to let you know, all these calculations that I'm showing, they all use the same radius of gyration. So you can think of a dumbbell and a kettlebell. Both are 25 pounds, but the dumbbell has the mass on the end of a stick, where the kettlebell is all round, condensed into as small as it can be. So although they weigh the same, the dumbbell has more inertia because the radius gyration is higher, which it's the dumbbell, the weights are on the end, so the radius of gyration is greater than the kettlebell, which is all condensed into a ball. So just think of all these here. We're not changing the dumbbell weight, we're changing a kettlebell. So the radius of gyration is the same, we're just increasing the mass. And also for all these, I'm using a coefficient of damping of 0.7. So the only thing changing here is the inertia and the mass, but the damping for each mode remains the same, the damping coefficient. So next we're going to look at different chassis stiffness distribution, but all have the same weight distribution and roll stiffness distribution. So here we can see the front of the chassis is lower than the rear. And here the front of the chassis is higher than the rear. So Like we can split front and rear roll stiffness of the suspension. We can do the same with the chassis. This is how the chassis stiffness distribution plays into your lateral load transfer distribution. So in the case where the front is soft, you get more rear lateral load transfer distribution. So if we look at the whole car, the chassis and the suspension as a system, the rear of the system is stiffer and we get more rear lateral load transfer distribution, which we'd expect. Same here where the front is stiffer, we get more front roll stiffness, lateral load transfer distribution because the system is stiffer in the front. So that's with a chassis frequency factor of only 0.84. So this is where the chassis is, the frequency is lower than the suspension frequency. And as we increase the chassis frequency, we can see that the lateral load transfer distributions start to be almost the same. So although the chassis stiffness distribution is changing, the lateral load transfer is not changing as much because, again, the front and rear roll stiffness distribution was 50%. So our theoretical lateral load transfer distribution would be 50. And we're getting closer to that number as we increase the chassis stiffness. Next, I want to look at the difference of the percent front weight, keeping the chassis stiffness distribution and roll stiffness distribution the same at 50%. So looking at the soft chassis, as we increase the front weight, we're getting more front lateral load transfer distribution. And as we increase the chassis stiffness, we once again get close to that 50% theoretical number. And so in case we see this blue line overshoot and come back, basically the rear inertia of the chassis is increasing the rear tire load before it comes to steady state. Next, we're going to look at damping, keeping weight distribution, chassis stiffness, and roll stiffness distribution all the same. So I kept the same front damping and I increased the rear damping, which we could look at percent front damping. So as rear damping increased, percent front damping distribution decreased. We can see at turn-in the lateral load transfer distribution went higher to the rear, which we'd expect because we have more rear damping. We'd expect at turn-in as the chassis starts to roll, damping needs speed to apply force. So it starts to roll, it gets that speed. There's more rear damping. It's going to put more load on the rear, which is what we're seeing here. And as we increase the chassis stiffness, we see that rear lateral load transfer distribution spike. But they all kind of do the same thing where with more rear damping, the lateral load transfer distribution goes more towards the rear. But as we increase the chassis stiffness, we can see how fast it adds on. Where here it goes little, probably we'll call it 47%, where, I mean, it's way off the chart here. I couldn't increase the chart, but you could see that it'd go way down. So although they all sort of have the same effect of increasing rear damping, the difference is how fast and how much it does it. So with a stiff chassis, there's a huge difference with this change in damping, which means, let's say you're on the racetrack with your car, you're making damper changes. A stiff chassis is going to react to those damper changes, where if you have a soft chassis, you may be doing quite a few clicks on your dampers and not getting that much of an effect. So the stiffer your chassis is, the more of an effect you're going to see when you actually start to change your damper settings. So here we're going to look at the effect of roll stiffness change, keeping weight distribution and chassis stiffness distribution the same at 50%. So this is kind of the same thing we're looking at in Excel, where we change our roll stiffness and we expect to see a change in lateral load transfer distribution, which we are seeing. So we change the front roll stiffness distribution. We'd expect to see more front lateral load transfer distribution, which we are seeing. And it continues, same trend. You increase the front roll stiffness, you get an increase in lateral load transfer distribution. But the difference, so we can see, if we just draw a line across, it's right about 52 to 48. But on the stiff chassis, it's maybe 53 to 47. So for the same changes, we're able to get more lateral load transfer distribution change with the stiff chassis, which is kind of what we saw in Excel, where the changes in your roll stiffness is going to correlate more to the expected theoretical like value without, when you don't take chassis stiffness into account. But the difference we can look at here, being a dynamic model, is the slopes of these lines, as well as how long it takes to reach its steady state value. So look at this, the least stiff chassis, the slope of that line. If we go to the stiffest one, where it's closer to vertical. So what this is if we take the time it takes to reach 5% to 95% of the steady state value would be the rise time. So it'd be the difference from 5% to 95%, so some kind of time. And also we can look at the time it takes to reach 99% of the steady state value. So somewhere around here would be the settling time. We would see as we increase the chassis frequency factor, the slope of the line starts to become more vertical, which the rise time is decreasing as well as the settling time. So we can plot those out just as bar graphs and see that the settling time generally decreases with chassis stiffness factor. And then the rise time also decreases with an increase in chassis stiffness factor. So we can take those bar graphs and then we can just look at a 2.5D plot of those, which may be easier to see. So let's take a given roll stiffness distribution, say 50%. And as we increase the chassis frequency factor, the settling time starts to go down. And same with rise time. As we increase chassis frequency factor, the rise time starts to go down. So as you increase your chassis frequency factor, the car is responding quicker. It's meeting that steady state value faster. So your car is going to feel more responsive during those times. It's not going to feel like it's lagging and taking the time to set. The driver's going to feel like the car is solid, like the suspension's working, since the chassis is basically acting more as just a bracket and less of a spring. So whatever changes that you'd expect from the suspension, as you increase the chassis frequency factor, those changes are going to have more of an effect. The chassis is going to be, we can call it getting in the way less as you make those changes. So what did we learn from this? Well, we know that now mass and stiffness of the chassis play an effect on all of this. So as you increase the mass of your chassis, you're going to want to increase the stiffness of it. As you increase the stiffness of your suspension, you're going to want to also increase the stiffness of your chassis. Because the closer the stiffness of the suspension gets to the stiffness of the chassis, the changes you have are going to have less effects, like we saw with the dampers. So it's not only about stiffness, but you got to look at the mass and stiffness of the car that you have. So think of like an off-road vehicle, which has softer suspension. Maybe it doesn't need as stiff of a chassis, where if you look at like a Formula One car where the chassis or where the suspension's really stiff for, aero reasons, you're going to want a stiff chassis. So the changes you make in the anti-roll bars and the dampers have an effect that you want. Well, now that we looked at this, we see rise and settling times, but how does that affect the car on track? Well, there's two ways you could go next after this. You can do a lap time simulation, which incorporates rise and settling times, or you can go and test with a car that you may already have. So here's an idea that I would have to test different chassis frequencies and how they affect the rise time, settling time, as well as lap time. So this is my frame for my Formula SAE car. What I would do, I'd weld in these different tubes. And I would start with it like this, and then take the torsional stiffness of the car. And to do this, I would use 3 scales. Let's say the car's rear heavy, so I'd put 2 scales under the rear and one on the front, and lift it up so this front left wheel, could just hang free. So we'd have a weight on this front scale. That times the track width would give us the torque applied on the chassis. And we can check it looking at the difference on the rear scales. One scale minus the other scale times the track width should also give us the same torque, because it just be opposite. You have a front torque, there's going to be reaction taken up by the rear. And then you can sit in the car, do it with the car empty, put sandbags, put a different person, just to get different torque values and see if the torsional rigidity is pretty much the same as you do those different tests. And then after, I would take the torsional rigidity of the car, I would go and do a step steer test. So drive straight, turn the wheel degrees. So let's say we go, turn 90 degrees and see how the car reacts. So we could look at lateral acceleration and yaw rate if we have the sensors for that, and get the rise and settling time for each of those. And then after doing that step steer test, we could also set up a course. In this case, it's Formula SAE. I do an autocross course and get the lap time for that. I then go in just with the Sawzall, cut that tube out. Again, measure the torsional rigidity, then do the step steer test, get the rise and settling times for acceleration and yaw rate. And then again, do the autocross course, get some lap times. And then cut that tube out, and then cut that tube out. For each setup of the tubes, again, you take the torsional rigidity, do the step steer test, run the autocross course, and get the lap times. And so I chose these tubes because the cockpit of the car is open. Because the driver has to sit here, it's harder to get tubes in there and make this center section of the frame stiff. But after we do that, you could also start cutting other tubes out if you wanted, to get different torsional rigidity values and see how that affects the car. You can also try to add more tubes in the front or more tubes in the rear to change that front rear torsional stiffness um, distribution, whether the front stiffer, the rear stiffer, or the middle stiffer. See how that affects your rise and settling times. And also, while doing torsional rigidity, you could take the angle displacement at different points. So you could add a angle finder here at the top roll hoop. You can put it across the floor, across the front roll hoop, and then across one of these bulkhead. And you get different angles for each one. And you can see, if you plot those, you can see how the angle changes across the chassis. And then you may be able to pinpoint a part of the chassis that's not rigid. Like if the difference between the main roll hoop and the front roll hoop was really big, then we know the center section of the car is not very stiff. But that's another thing while you're doing this test, or while I'm doing this test, I could see. So unfortunately, my car isn't running, and also I'd have to find a spot, a big parking lot that someone would let me legally use to do this test. But I'm hoping in the future that I can revisit this and try it out to see how my model, this transient model, relates to real life for these rise and settling times and how that affects the actual vehicle handling and most importantly, the lap times. So really all of this that we do in simulation is to change the vehicle balance to be able to tune the balance, lateral, maximum lateral acceleration, braking, all of that, as well as lap time. So I'd like to see apply this transient model that I did and see if how that applies to lap times. And then at that point, we might be able to find what chassis frequency factor is enough. So if we could actually go and test this, we can find how stiff does your chassis need to be. I wish I could test that now and have the answer, but I at least wanted to share this and maybe someone else can test it before I get to do it. Or maybe someone has experience with this and they kind of have a better idea of how stiff does your chassis need to be. So that's a question I've seen asked a lot, but a question I haven't actually seen answered. So if you've seen anything, leave a comment so we can start a discussion of this. We can all combine our knowledge and experience to this discussion.